Okay, now we are back with more energy than ever than before to just fill out the second block, which is an essential blocks in our parametric Bayesian, writing it that in the stand file. Okay, what do we mean by the parameters? If you are clear at that stage in your design of the experiment that what kind of parameters that you have defined, definitely this block is going to be very easy to define it. Why? Because in order to do that, I'm just going to take you back to the whiteboard that I created that for you on the lecture that we just called that Parametric Bayesian Inference and Estimation. You saw that I talked that we have, for example, we have a pair of the woman weight and the height. We said that in the non-Bayesian we talk about this model, but in the stand we said that we think of the height as a normal distribution, which we have two parameters for that. The nu, which defines the mean of the woman's heights, and also the sigma, which is a measure of the dispersions around the central tendency measure, which is going to be the nu. We said that essentially the name of the parametric Bayesian comes from the fact that even though that we can just have a clear and explicit value for the sigma, normally we define, I should say, the parameter nu as a model. For example, the model that we had height, it's a slope times weight plus b. It can be defined as a parameter of the mean. We say that the nu, that it's going to be the mean of the normal distribution of the woman's height. That nu is going to be modeled as slope times the weight as a variable plus b, which is a linear model with respect to our only variable, which is weight. Then as a result, when you look at this model, how many parameters you can find it here? I mean the parameters that we have no idea. One of the parameters is going to be the slope. The other parameter is going to be the intercept. Because we have no idea how much they are, A is something we have no clue, and B the same thing. Like essentially the thing that we did in the non-Bayesian context, that we had to use ordinary least squares to find the best estimates for the slope and the intercepts. The same thing here, A and B, they have to be determined, they have to be estimated. Then the first two parameters of our model is going to be one A and one is going to be B. And also we have another parameter in our model which is going to be, let's say, for example, the sigma, which is the measure of the dispersion around the mean in our normal distribution. Then we have three parameters. Then as long as you have a clear understanding how the model has been built, then now it's going to be very easy to go back to the block of the parameters in the stand file to define the parameters. The first parameter which I'm just going to define, I'm just going to define a parameter. I'm just going to move from left to right. I'm just going to first define the parameter for the slope, which is going to be, let's say, that is going to be the intercept. Let's call that parameter alpha. Alpha is a parameter. Please take care to this part of the lecture, because when we just go back to just want to just make, I should say, the inference and the estimates for the slope, it's crucial to remember what did you call the parameter for the slope. If I had A here, something close to that alphabetically is going to be the alpha. A and alpha sounds so close. If I call the parameter which defines the slope of my model alpha, then I know that it's going to be a real number. Then it's going to be crucial to distinguish that in the model that we have. Then the parameters as alpha, which defines, I should say, the slope of my model, I call it alpha. It's a real number. Remember, make sure that you have semicolon to close that line, and I'm just going to go as a note, the parameter for the slope. That's crucial. And also the same thing for example, the parameter of the intercept, because the intercepts also, was defined as a parameter that we have to find the best estimates for it in our model. And that's why essentially we are here to just do that parametric Bayesian inference then now for the intercept, which we call that as a B, I'm just going to call the parameter as a beta, because B and beta sound so close to remember them in future. Then I call that beta. Then I know that this parameter is also real. It can be real. That's right, because for the intercepts that you have, it can take any real number. You can just remind yourself from the basic math that you have learned even from the high school. The B, the intercepts, it's on a real number. It's on the real axis. Then that's why we just define it as a real number at the parameter block inside the rstan script. Then I know that I should not forget to put the semicolon there, and at the same time I'm just going to write a note. I say that the parameter for the intercept. Remember, these two things is crucial. I just want to go back. I hope that you'll listen to my word right now. In the next couple of tutorials, when we have, I should say, we are just going to go ahead to find the inference, to find the best estimates. We are just going to go to the posterior distribution. Then we have to extract this value. Remember, this one is crucial to remember which one was which. The slope was defined as alpha and the intercept was defined as beta. Also, we have another parameter. The other parameter which we have is the sigma. The sigma, as I said, it's the measure of the dispersion around the central measure that we had, which is going to be the mean of the mu. Although we do not look at it as a parameter which is modeled, but still it's a parameter which has to be defined. Because look at that. In the normal distribution that we had two parameters. And if you ask anyone who is a little bit, I should say, knowledgeable about, I should say, the basic statistics, you ask him how many parameters defines a normal distribution. They write back to you and say that, okay, there are two parameters that they define the normal distribution. One of those parameters is going to be the mu, and the other parameter is going to be the sigma. In the Bayesian model that we have, we model the mu as a parameter of the normal distribution. We model it by a linear equation, but we do not model the measure of I should say, the dispersion around the central mean. We do not model this one. Then although we do not model this, we still have to define it. Then I just go here. I now know that the dispersion can be a real number also. Then that's why we put that the real, and I just call that, I call this sigma, and I put the semicolon, and I put the description here, the standard deviation, or sometimes you can, in abbreviation, you call that SD, anything you want. But however, before we finish the parameters line, sometimes which is very customary is that you restrict, I should say, your parameters when you talk to Stan, and you say that the sigma, the measure of the dispersion, has to be a positive number. You just want to restrict it only to a positive, a real number, but a positive number. That's a restriction we are just going to impose on the parameter sigma. Then as a result, in order to talk with the language of the Stan, to the Stan, I'm just going to use it like that. I just put the restriction, I put these two things together, I just go inside, and I put that as a lower bounds, I equate it to be equal to 0. And if you just want to just restrict it even from the top, you can say that upper also equals, for example, to 1. Anything you want. We do not want to restrict the upper bound. Then I'm just going to go ahead to erase the upper restriction and just keep the restriction as the lower only. Then in this part, it means that the model, the parameter block, which is for the model that we have. To model the height of a woman with respect to its weight, the parameter section is complete. Why this is complete? Because if I go back to the model which we have created, we see that we only have two parameters. Because we have nu, which is modeled linearly with two parameters a and b, and also the sigma as a standard deviation. By saying that, our block for the parameters is finished, and now we should just take a deep breath, say, thanks God, this is done. Go to the next block, which defines essentially the model that we have. Then I think that's a good spot to just stop this tutorial right now. Then we go back fresh with more energy to just go ahead how to fill the model parameter in our rstan file. Then I should say I see you on the next tutorials, which I'm so excited to see you then there.